All right, let's jump right in. Today, we're diving into a story of two chemical opposites. And the craziest part, they're literally all around you, hiding in plain sight. Think your kitchen, your bathroom, even the food you eat. We're talking, of course, about acids and alkalis.
So, here's what we've got on tap. First, we'll get a quick introduction to these opposites. Then, we'll do a little character study on acids, and then on alkalis. After that, we'll uncover a secret ingredient that makes it all happen. And finally, we'll see how all this chemistry actually works in your daily life.
Okay, let's get started. First up, an introduction to opposites and the hidden chemistry right there in your home.
So, let me ask you something. What could a fizzy drink and, say, a bottle of household cleaner possibly have in common? I mean, they seem like they're from different planets, right? One's for drinking, the other, well, you definitely don't want to drink that. But what if I told you they share a really fundamental connection?
It turns out they're chemical opposites. That's the link. The soda gets that tangy kick from an acid. And that powerful cleaner, its power to cut through grease comes from an alkali. They're basically the two main characters in this whole chemical story.
All right, time to meet our first character, the acid. And if you've ever bitten into a lemon, you've already had a pretty good introduction to its most famous quality.
So, what is an acid, really? In scientific terms, it's any compound that, when it dissolves in water, lets go of hydrogen ions. You'll see those written as H+. And that little H+ ion, that's the secret sauce. It's where all of an acid's powers come from.
Okay, but here's the thing. Not all acids are the same. You've got your strong ones and your weak ones. Think of a strong acid, like hydrochloric acid, as being super generous. It gets in water and bam, it releases every single one of its hydrogen ions. A weak acid, on the other hand, like the citric acid in that lemon we mentioned, is a little more stingy. Only some of its molecules are willing to give up their H+ ions.
So, acids have some pretty cool party tricks. One of their signature moves is how they react with certain metals. It's actually a pretty straightforward recipe. You take a reactive metal, say magnesium, you add a bit of dilute acid, and what you get is a salt plus a whole bunch of hydrogen gas bubbles.
And here's another classic acid reaction. This one's with carbonates. You've definitely seen this one before. It's the science behind that baking soda volcano you made in school. An acid plus a carbonate, like baking soda, gives you salt, water, and a ton of carbon dioxide. That's where the fizz comes from. And if you're a bit of a chemistry nerd, you can see the ionic equation right here. It shows how those H+ ions from the acid hook up with the carbonate ions to make water and that CO2 gas.
Okay, so we've gotten to know acids pretty well. Now it's time to meet the other main character in the story, its polar opposite, the alkali. So what exactly is an alkali? Well, it's a special kind of base. The key thing is that it has to be able to dissolve in water. And when it does, it lets go of hydroxide ions. You'll see those written as OH-. So if H+ is the acid's calling card, then OH- is totally the alkali's signature move.
And alkalis have a completely different vibe. They usually taste bitter, and they have this really unique, slippery, almost soapy feel to them. But don't let that fool you. That slippery feeling can be deceptive. Strong alkalis, like sodium hydroxide, you might know it as caustic soda, are incredibly corrosive. And, just like acids, once they're dissolved in water, they create ions, which means their solutions can conduct electricity.
Alkalis have their own signature reactions too. A really cool one is that they form these solids called precipitates when you mix them with solutions that have metal ions. And what's really neat is that different metals give you different colors, which is super useful for chemists trying to figure out what's what. For instance, you can see here, if you add an alkali to a copper solution, you get this cool blue gelatinous solid. But do the same thing with an iron solution, and you get a green one instead. Pretty neat, right? So, what happens when these two opposites, acid and alkali, finally come face to face? Well, you get the climax of our story, neutralization. It's actually pretty simple. The H+ ions from the acid and the OH- ions from the alkali get together and form water. They basically cancel each other out, and all you're left with is salt and water. But wait, there's a twist, a big one. It turns out that for our characters, for the acids and the alkalis, to do any of the things we've talked about, they need a secret ingredient. Without this one thing, they're completely powerless.
So, what is it? Think back on everything we've discussed. What's the one thing that's been a part of almost every single reaction? What is the one thing these chemical opposites need to show us what they can really do?
Let's look at the proof. Check this out. If you take some dry citric acid crystals and touch them to a piece of dry blue litmus paper,
which is just a chemical indicator, nothing happens. It just stays blue. But the second you dissolve those exact same crystals in water, that solution will turn the litmus paper red instantly. That's proof it's acting like an acid.
And here's another great example that drives the point home. Take hydrogen chloride gas. If you dissolve it in something that isn't water, like methylbenzene, it doesn't make any ions. The solution won't conduct electricity at all. But dissolve that same gas in water, it immediately breaks up into H+ and chloride ions, and suddenly you've got a solution that conducts electricity like a champ.
So have you figured it out? The secret ingredient is water. That's it. Without water, these compounds just can't ionize. They can't release their H+ or OH- ions. And if they can't do that, they can't be acids or alkalis. You could say water is the stage where this whole chemical show takes place. All right, for our last section, let's bring this all together and see how this whole story of acids, alkali, and water actually shows up in your everyday life. Think about something like a fizzy drink powder. In the packet, it's just a dry mix of a solid acid and a carbonate. It can sit there forever, no problem. But the instant you add water, our secret ingredient, the acid finally releases its H+ ions. Those ions react with the carbonate and boom, you get all that carbon dioxide fizz. It's the exact same idea with baking powder. That CO2 gas is what makes your cakes rise and get all light and fluffy.
Now this chemistry is really fascinating, but we have to talk about something super important. These characters have a seriously dangerous side. When they're concentrated, both strong acids and strong alkalis are extremely corrosive. We're talking severe chemical burns to your skin or anything else they touch.
So this brings us to a critical safety rule. If you ever spill a concentrated acid or alkali on your skin, the very first thing you do is get that spot under slowly running cold water. And you keep it there. You keep rinsing until the pain starts to fade, because that's what dilutes the chemical and washes it off. And of course, for any severe burn, get medical help right away. No delay. So there you have it. We've met our chemical opposites, we've seen what makes them tick, and we've found the secret ingredient that makes it all possible. So, I'll leave you with a final thought to chew on. Now that you know the rules of the game, where else do you see acids and alkalis at work? Or maybe even at odds, in the world around you?